Hi everybody, and welcome to our second video on integration by parts. In this video, we're going to see a different application of integration by parts. This time, it's not when we exactly have a product in the integrand, but rather when we have a function as our integrand that we would rather differentiate than anti-differentiate. Let's see an example. So say I wanted to find an antiderivative for the arcsine function. So I don't know an antiderivative for the arcsine function, but I do know a derivative of the arcsine function. So how can I use integration by parts? Well, in integration by parts, you're going to set one part of your integrand to be u. So let me call the arcsine my u. Why? Because the next step when I make my table, u equals arcsine of x, is to compute du, meaning I need to take a derivative of arcsine of x. All right, can we remember it? Derivative of arcsine of x? All right, I'll give it to you this time. The derivative of arcsine is going to be 1 over the square root of 1 minus x squared, and then we never forget our dx's, okay? Our d's always come in pairs, either with another d or with an antiderivative sign. All right, now, I set up my u, I set up my du. What's my dv? Well, there's not much left. There's a dx. That's got to be my dv. So, if my dv is dx, finding an antiderivative of dv, I get v. Finding the antiderivative of dx, I get x. And now I can apply my integration by parts formula. Let's write that down quickly. Antiderivative of u dv is uv minus antiderivative of v du. All right, so if I want to use that here, first thing I need my uv. So u times v, that's going to be the x times the arcsine of x. All right, what's next? Oh, I need to subtract an antiderivative. Find v du. So here's my v, here's my du. So I need to do antiderivative of x times 1 over the square root of 1 minus x squared. And of course, we never forget our dx on the end. Now, I've replaced an antiderivative that I did not know how to solve with an antiderivative that at first I think I still don't know how to solve. But there's something really nice here. Notice this function, 1 minus x squared. Its derivative is negative 2x. I don't quite have negative 2x here, but I could make it so that I did. What if I just snuck a little negative 2 in front? Hey, then I've got a negative 2x. Of course, that's cheating a little bit, so I'm going to have to divide by a negative 2, and I'll put it outside the integral. The reason I do this is that now I can do a substitution. All right? The substitution here is going to be, well, we won't use u. That's normally our substitution letter, but we already have a u. So let's use w. w equals 1 minus x squared. If I do that, then dw will be negative 2x dx. That's why we wanted that negative 2 in here. So I can rewrite my antiderivative. So let's just copy what we had. So we have x times arcsine of x minus our antiderivative. Oh, we had a 1 over negative 2, so I'll make that into a plus 1/2. Now, the negative 2x dx, that just becomes dw. So we'll stick a dw at the end. And then I have 1 over the square root of w. Okay, square root of w, that's w to the 1/2. 1 over the square root of w, that's w to the negative 1/2. Okay, you could leave it in this form, but man, I do not like square root signs when I'm doing my calculus. All right. Okay, so now I can just use a power rule here. I get x arcsine of x plus 1/2. All right, now let's see. You have to add 1 to the power, so that would be to the 1/2, but then you have to find the reciprocal of 1/2, that's 2. So times 2w raises by 1 to the 1/2 power plus our constant of integration. Okay, a little bit of simplification here. 1/2 times 2 is equal to 1. And now I have w's, but of course I want x's in the end. So I'm going to back substitute and end up with, let's see, w was 1 minus x squared. There's a 1/2 power. Okay, fine at the end. I guess I'll put my square root sign back in. square root 1 minus x squared plus our constant of integration. So this is really phenomenal. We had an integrand. We had no idea how to find an antiderivative. And so instead we differentiated it. And somehow integration by parts lets us get an answer. That is really, really awesome.